Alright, hello everyone. My name is Johannes Pekkila and today I'm going to talk to you a little about what I've been doing this summer. So basically, long story short, I've been doing FMM on GPUs. I can imagine some of you are there like, what are FMMs, what are GPUs, why do I care? Well, I'll tell you, it all boils down to particle-particle interactions. Imagine a galaxy full of stars. Imagine a second galaxy and imagine these galaxies colliding and exploding. That's what we can simulate with the fast multiple method. Or we can go to atomic scale, like these tiny atoms with electric charge, and we can simulate how they move around, like in a fission or fusion reaction. And so basically this is an n-body problem. So we have this n number of particles and we want to simulate the interactions of them. And basically the naive solution is quite complicated because you take this one particle and then you have to check all the other particles, what kind of force they exert on this particle or whatnot. But with the fast multiple method we can reduce this complexity greatly. And since we are here at Uli Supercomputing Center, why not use the state-of-the-art GPUs and whatnot to accelerate this problem further? So that's what I've been doing this summer, and even if I say so myself, the program is now lightning fast. Okay, so this is how the fast multiple method works. It consists of 5 steps: multiple to multiple, multiple to local, local to local, and whatever. And actually we don't really care about 4 of these. The bottleneck is multiple to local. It takes the most time. This operation consists of 3 subroutines, which are forward rotation, shift, and backwards rotation. And the cool thing is that once we optimize these, we can actually use the same algorithm for several other operations, for example multiple to multiple. So you could say that it's the same shift but different operation. So, and the most important part is the forward and backwards rotation, and we are going to look into them next. Okay, so here's the rotation operation, and basically what we have here is a triangle and a pyramid, which is basically the rotation matrix. And we have the rotation operation we do, and we get yet another triangle. So let's trace a few steps. So if we want to solve the output at 0, we need to fetch the value 0 from the input triangle and the value 0 from the rotation matrix. And next we solve the element at 1 in the next column, and suddenly we need more input elements from the input triangle and also from the rotation matrix in order to solve the output. And finally, in the last column, we need even more values to solve this. And basically what's difficult here is that when we compute the output for each element in the triangle, we really can't use any of the values in the rotation matrix. We always have to fetch a new value. So that's what we are going to remedy next. Okay, so what do we have here? We have the same triangle as before and the same rotation matrix, except that we have stacked the triangles in this very stack looking shape. And the memory of the GPU is very slow. We want to minimize reading from the GPU's memory as much as possible. So the good thing about this approach is that if we have multiple triangles which all use the same rotation matrix, then we can fetch the rotation matrix only once from the memory of the GPU and reuse it in the caches and solve multiple triangles at once. And this is very fast. So that's it. that's the last multiple method and the rotation operation in a nutshell. Obviously there's much more stuff I didn't talk about. I'll talk about them next time. I hope you enjoyed this video and I wish you a pleasant